In today's session, we'll review an insightful research paper titled A Novel Deep Learning Framework for Intrusion Detection System, authored by Mahwish Amjad, Hira Zahid, Sania Zafar, and Tariq Mahmood from the Institute of Business Administration, Karachi. This paper proposes a hybrid deep learning model that combines autoencoders and long short-term memory (LSTM) networks to detect both known and unknown cyber intrusions in network traffic. By the end of this video, you'll understand the motivation, methodology, experimental setup, results, and future prospects of this study. With the exponential rise in internet-connected devices, network security has become critical. Detecting malicious network activity, known as intrusion detection, is a top challenge for cybersecurity researchers. When it's increasingly difficult to identify malicious activity, or what we call network intrusions. An intrusion detection system, IDS, is designed to monitor network or host activity and detect such intrusions. There are two broad types of IDS: network-based IDS, NIDS, which monitors the entire network's traffic. Host-based IDS, HIDS, which analyzes activity within a computer system. We have discussed the two types of IDS. Moreover, detection mechanisms themselves can be of two types: anomaly-based IDS, AIDS, flags suspicious activity differing from normal patterns, capable of detecting unknown attacks. Signature-based IDS, SIDS, identifies attacks based on predefined patterns, efficient for known attacks. Now here's the challenge. Real network traffic can contain both known and previously unseen attacks. Attackers constantly evolve their techniques, meaning it's impossible to predefine every possible attack signature. Hence, there's a need for a system that can detect both known and unknown attacks simultaneously, and that's exactly the gap this paper addresses. Traditionally, machine learning algorithms like support vector machines, SVM, random forests, and discriminant analysis have been used for IDS. Later, semi-supervised techniques were explored to handle both labeled and unlabeled data, because in real-world settings, not every attack instance is labeled. However, as network data became larger and more complex, the research community shifted toward deep learning approaches. Researchers experimented with deep belief networks (DBN) for unsupervised detection, recurrent neural networks (RNN) for time series modeling of network traffic, and even semi-supervised ladder networks for hybrid detection. Despite these advances, only a handful of studies tried combining unsupervised and supervised deep learning models together. This paper fills that gap by integrating autoencoder, unsupervised, with LSTM, supervised, to form a semi-supervised deep learning framework for intrusion detection. An autoencoder is an unsupervised model that learns to reproduce its input. It compresses data through a bottleneck layer, and large reconstruction errors often signal anomalies. LSTM, or long short-term memory network, is ideal for time series data like network traffic. It remembers long-term dependencies, helping classify types of attacks based on sequential patterns. Used a benchmark dataset for IDS with over 125,000 training and 22,000 testing samples. It contains 41 features and 4 major attack categories that are denial of service, DOS, user to root, U2R, remote to local, R2L, and probe attacks. The framework works in 2 stages. Stage 1, anomaly. Detection using autoencoder. Incoming network packets are first processed by an autoencoder. If the reconstruction error is low, the traffic is normal. If the error exceeds a threshold, 0.0025 in this study, it's flagged as anomalous. Stage 2, attack classification using LSTM. The anomalous traffic is then passed to a trained LSTM classifier. If the pattern matches one of the predefined attack categories, it's labeled accordingly. If not, it's marked as a novel or unknown attack. This combination allows the system to detect both known and unknown intrusions efficiently. The architecture was fine-tuned through extensive experimentation. Autoencoder achieved 96% training accuracy with 2 encoding-decoding layers, KNH activation, and mean squared error loss. LSTM achieved 96.8% accuracy using 3 hidden layers and a dropout rate of 0.1 to prevent overfitting. In experiments, the researchers trained both models independently and then tested the combined system. The key findings are mentioned. This happens because the errors from both components compound. If each module has a small inaccuracy, the integrated system inherits both. Still, an 82% combined accuracy on detecting both known and unknown attacks is quite promising, especially considering the framework's novelty. The paper also demonstrated visually that reconstruction error decreases steadily during training, confirming that the model learns effectively over 100 epochs. Test samples are passed into the trained autoencoder and LSTM. Autoencoder had been initially trained with only normal records for training purpose, but for testing, both normal and abnormal records have been passed in trained autoencoder for classification purpose. Samples, which are recognized as anomalous by autoencoder, are passed into the trained LSTM module. LSTM identified particular attack category of anomalous packet. Those attack patterns which could not be found in the predefined list of LSTM have been labeled as novel attacks. The paper contributes several important ideas to the field that are combining unsupervised and supervised deep learning in one IDS framework. Also, the system can detect both known and unknown attacks, something many IDS models fail to achieve. The detailed parameter tuning, use of NSLKDD dataset, and accuracy comparisons validate the method's robustness. Since LSTM handles sequential data efficiently, this approach can eventually be adapted to real-time intrusion detection systems. However, like any research, there are areas for improvement. The testing accuracy, 82%, leaves room for optimization, possibly through better hyperparameter tuning or advanced architectures like CNN-LSTM hybrids. The system is tested only on a benchmark dataset, not on real-world network data. Real deployment could reveal more challenges like noise, latency, or imbalance. Also, the framework's scalability for large enterprise networks is not yet explored. The authors acknowledge these points and plan to test the model on real network traffic and further reduce the inaccuracy rate of both autoencoder and LSTM in future work.